So I'm working as part of the CCID project, which is continuous crystallization, isolation and drying. And the objective of this project is to have an integrated platform for continuous technology. It is funded by a group in Ireland called Enterprise Ireland, and it's a joint project with the SSPC. We have 2 years and we have 2 industrial partners on the project too. So our problem statement, we want to take a batch crystallization for an industrial API, so a real-life API, not a model compound, and transfer that to a continuous crystallization process. We want to maintain the yield, form and particle size specifications from our batch process, and the plan is to produce about 50 kilograms of product over 100 hours in the pilot plant without any operability issues and meeting our specifications. And we have a fixed equipment set for this work, and we have access to 3 20-litre reactors, so we're going to operate our continuous crystallization as an MSM pure cascade. And the idea is to have a flexible methodology and equipment set that can be used for future crystallizations, not just this particular API. When we reduced our initial concentration, we could see straight away that we weren't going to meet our yield. The solid loading was still too high at 22%. And then also we had a high throughput issue for our fixed equipment set. So we wanted to go back and look again at our solubility. So we did some solubility modelling in Dynochem, and this helped us choose a new solvent matrix that would meet our requirements better. So you can see here that we were at 50-50 acetone and water, which is about here. We were coming in at 55 degrees and we were right up here. So what we did was we moved across here to a higher acetone ratio. Now we didn't want to go completely acetone because we wouldn't have the solubility at the higher temperatures to get a yield. So if we went to 25%, we found that we could start with an acceptable concentration and have a good endpoint to meet our percentage yield. And also our throughput would be much more manageable and our solids loading. And there's a link here to this tool if you would like to use it in future. It's just completely inefficient to do this in the lab, and it takes far too much material and time. So, and cost and a lot of people in the pilot plant. So we want a different approach. So we have to model the system, and to do that we need our kinetics. So in parallel to the pilot plant work, we began to look at different ways of understanding the kinetics of our system. And if you're lucky enough to have your growth and nucleation kinetics, you might have a very straightforward time designing your continuous crystallizer. So we had to do desupersaturation experiments to get our growth kinetics, and then we did some single MSM pure operations to get our nucleation kinetics. And so this is a model of the 2 CSURs. So the other ones were just a single MSM pure. So we took the kinetics from these, our growth kinetics and some fitted nucleation kinetics, and we tried to model the 2 the double CSUR. So that's where the first one's at 37.5 and the second one is at I think we put it in as 3 degrees in the model. So you can see here again the things we're looking to predict are what is that operating concentration in crystallizer 1 and crystallizer 2, and how does that compare with our experimental data or data from our pilot plant, and then our particle size. So, and then time to steady state. So if we look at the product concentration in crystallizer 1, we can see it here, this triangle, and it's very close to our predicted concentration. So that's our product concentration here. So you can see that this is at 78 grams per kilogram, which is very close to what we had. So we were very happy with this data, and this is probably a sign that our growth kinetics are quite good. And then again, with our product concentration in crystallizer 2, you could see here, it's predicting it quite well again. So you can see as well, if you compare it with the particle size data, you get to steady state with regard to dissolved concentration before you get to particle size steady state. And this is quite representative of a real system as well. And how does that affect that time to steady state with regard to particle size? So one of our big focuses now is going to be this volume in crystallizer 2. So if that's 3 times the size of our volume in crystallizer 1, we should get a larger yield. And then also the effect of agitation, so that we can understand the secondary nucleation and manipulate that to get the particle size that we need. So I would say that it's all very much a work in progress. The project's not finished yet, so we're still working away.